Okay, so we are ready to start. Hi, everyone. That's what we're going to talk about today. I'll switch to my slide template. Don't worry. I had to warn you about questions. Please feel free to raise your hand, or you can use Slido as regular today. I'll answer Slido questions in the end of the talk. So who I am and why we're talking about containers here. I work in a company named Bellsoft. Formerly, all engineers there are ex-Oracle guys. And we produce our own binary distribution of OpenJDK called Liberica JDK. And one form of distribution of this binary is a form of Docker containers. Why do we need them? Of course, we need them to run our applications, run our microservices. It's quite typical nowadays to make your big application consisting of a lot of microservices and to deploy them using helpers, using containers. Sometimes it may lead to specific problems, like you see that some service may fail and you don't know why, at least when you start working with the technology. That's what we'll see today. I'm going to break the same simple service a few times to let you see that it's not scary, it's fine, that's something that happens to everyone. If you want to know more about containers, please visit Kensai Talks. And if you want to find more about container diagnostics, see Sasha Goldstein's talks. I'll just briefly stop here to remind that, yeah, very important point is that container is not a virtual machine. It is some tool that helps us to manage operating system resources using mechanism of the operating system of Linux. It is a hint to application, and it is a grasp for the operating system that runs a process to separate resources between processes, to isolate them, and to help manage system where many specific processes exist at the same time. Of course, it's worth mentioning two main mechanisms of Linux containers. It's namespaces and cgroups that allow us basically to describe what process may use and how much of that something process may use. And again, it's not a virtual machine. Specifically, then some container runs. The kernel that runs underneath is a kernel of current operating system, right? Please remember that. So if we talk about systems that manage containers, they just help us to use that kernel mechanism. For example, Docker, that allows to describe configurations for containers, to apply them, to see some information about processes and to manage that processes running in containers. And on top of that technologies, there is a huge stack of other things that allows us to deploy a lot of containers, like Docker Compose, to build clusters, like Kubernetes, and all things, all kinds of stuff. If we imagine some random process, it's not a big thing to put it in container. Actually, any process in Linux is already running in container, if it's running. And we can put it just in some other container. But if the process is just, it doesn't care, something may happen, and process may even not notice it, because it will die, not like in this picture, but it will just end up execution. But that's the behavior of the operating system. And one of such processes is Java. Java is not unique. It is a program, and we run it as an operating system process. And this process specifically is determined to run other specific programs expressed as a bytecode, for example. And in general, it's not so obvious to expect knowledge of containers from some system, from some program, like JVM. It is a complex system that has interesting requirements for resources because it creates threads for its own service needs. It grabs memory, not how user has written in his program or her program, but for its own needs. It's a big system. From the other side, we expect that when we deploy such a mature technology using another mature technology, everything will work perfectly. Like we expect that, yeah, why do we deploy, for example, microservices in containers? To make testing easier, to make our environment more reproducible, because we should not care about additional files or something. Let the operating system do that for us. We just describe that we need an isolated space. And on the other hand, when we run Java, we are stick to all the Java tools, management, monitoring, debugging. We wish to look at JMX information, to use JPS or JCMD or JConsole, whatever. But Java started to support containers not so long ago, starting from Java 9. And you can see that it all started with the very basic things. There are two important resources that we sometimes limit. Then start in containers, it's CPU and memory. And specifically in Java, the number of available CPUs has an influence on so many things. On third-party libraries, on number of GC threads, on default thread pool, on number of compiler threads, a lot of things. And also, that information is very important during certain phases of the VM lifecycle. That's CPU. And also memory. We should not run out of memory because we'll see it leads to really big problems. So the most simple thing is at least to look how much heap we can allocate than running in container. So in JDK 10, the initial work was sometimes redone, improved, made more standard, like standard logging, other kinds of things. Some not so well implemented things were deprecated. And again, it's support for CPU and memory limitations, but also the important thing that I mentioned, that's ability for standard management tools to work. Because then you use like some vanilla Java 8 or Java 9, your JPS command won't see run in Java process if it's running in Docker container. That's not good, right? Long way, and now Java 11, where, again, some things were redone, like deprecated functionality has been removed. You've got more information about current knowledge of container inside Java. You get finally working management tools. And if you limit CPU in, for example, Docker, there are multiple ways to do that. The most tricky thing is using CPU shares, but probably it's the most powerful and right way. And it was supported in JDK 11. Is that fine so far? How do you feel? How many of you use JDK 11 in production? And others probably use like 12? Yeah. Others probably use JDK 8, also known as the very best Java version ever. But there is a small problem. I started with JDK 9, so no support was introduced in JDK 8. But JDK 8 updates got backports from 9, 10, and 11. And during that backports, for example, options related to containers were implemented accordingly to the source of the backport. So in some updates of 8, you see functionality working like JDK 9, in some later like 10, and the latest is like 11, but not next. If you're happy with that, no problem. That's a good sign. That's normal. But work hasn't stopped. You can see that interesting and complex features were introduced in JDK 12 and 13. For example, in 12, there's an option for G1 to return unused memory. Imagine the system where there's a sum of memory limits for all running containers exceeds the physically available memory. And in fact, that's not a problem, because most probably every container will underuse resources if it's running fine. It either fails or it has some gap. And in case then you have unused memory, like you do garbage collection, and you can give that physical memory to other containers, other processes. That's the case. And as I mentioned, you can use command line to see some information available to the container about operating system, because it just hints. It says, yeah, that are your limits. And then container exceeds some limits, operating system just kills it. But it's container's responsibility, the processor's responsibility not to exceed the limits. And then we want to see what are current environment inputs about that in our Java process, like to look at JMX. We also want to look at it in a nice way using mission control. So we need support in mission control separately. And to store some information probably in flight recorder. So imagine we have an intent to deploy our application using containers. We can use old well-known systems to develop, to build, and to deploy our application. But let's look what's inside. So that's kind of parody to a Docker container, consisting of some information, a Docker image, where we have underlying operating system, of course, which is not shown here. We need Java runtime, and specifically business logic related to what our service does, and required libraries that are typically Spring and other stuff. Nowadays, microservice may require hundreds of libraries. So I totally agree that the keynote where, micro means that there is not many information input and output points in the service, but it's not so small itself. It may be quite a big program. And these parts can be combined for an interesting purpose in different ways. We can build an image as a monolith, as a single layer one, and make deployment using that big image. Or we can look that libraries are not changed too frequently, and we can speed up deployment by splitting, breaking that image to layers, keeping libraries separately. But in this case, default Spring Boot behavior, then it packs everything in an Uber jar, is not compatible with the approach. So we'll need to unpack it and, for example, to store libraries separately. And sometimes this is an advised approach. For example, then you try to speed up it a little to make startup shorter, for example. And we'll look at it today. But what about underlying platform? You have to get Java somewhere. It's now an interesting time because we have a lot of providers, and Bellsoft is one of providers. But you cannot use, for example, Oracle Java for free in your production. And you won't find freely available images for that, because that's the new policy. But you can get base images for free. And I'm personally sure that it's the right way to do things, just to use mostly standard images. Sometimes you need to save a few megabytes, so you can use JLink to create custom runtime. But again, you need something as a base. By the way, who uses custom runtime images? All right, so that's like a standard percentage, about like 5 to 10%. Yeah. You see that there are two columns. Sizes of JDK for 8 are about the same as 11. That's the sizes of images for x86-64. And for 11, there is no JRE anymore, at least from Oracle and Bellsoft. But you can use specially pre-built image that will be even smaller than JRE, and it's kind of standard image that you can use as a base. Let me show you how it works. So you can go to Docker and read the instructions. There are 3 variants of the image that you can build. It's base, which is very minimal and allows you to run just Java base module. Maybe not so useful. Light, that's about 100 megabytes. And full, which is also not so huge. So we can do it right on my machine. So just swept the old image created before, and we can just use the Docker build command basing on the Alpine, basing on the Docker file that we've downloaded. That will work relatively quickly. So you can get Java 8, Java 11, and also all intermediate versions, like 12, which is not an LTS version, for multiple operating systems, including, of course, Alpine Linux and Alpine Muscle. Muscle is an implementation of standard C library, which is much smaller than libc. But you have to use specifically built JDK to work with this base library. So it ended up, and you see the size, it's 37 megabytes. So if you really, really need your custom runtime image, tell me why. All right, so let's look at how services live and die in containers. So I have a small service, which is a standard example of Spring Actuator. So service does nothing, but it just waits 17 megabytes in a fat jar. And we can start it. You see Spring Boot starting. We can go to browser and look what it'll answer. Still no response because it's still starting. Are you familiar with the problem? It's maybe a bit dark here, but I think you are. So it works. And in another tab, I have JMeter that sends requests to that URL that I've shown you, the main URL, not diagnostic, but a very simple one. So the service works. And they see that it starts from like 10 requests per second, that it goes up to 20. The service is deployed on remote machine with public IP in a bare metal public cloud, and I run JMeter on my laptop. That's a simple configuration. All right, so no containers here. Let's run something in a container. But for this example, let's put some limit. Let's put container memory limitation of 5 megabytes. How do you think what will happen? Yeah, it won't start. So it's trying hardly to start and silence. Not a good behavior in Java world, but we need to check what happened. It's not so hard. Just check the system journal and we'll see that out of memory killer came and killed our service. By the way, I'm here as a non-root user, so I have to add my user in Docker group and the group that's allowed to read the system journal. All right. Maybe we'll try something smarter. Let's first of all check that our assumption is right. Let's look at Java flags. And we see that potentially used heap is huge. So it just uses all the heap. And the same is, yeah, some question? Yeah, sorry. And the same is for threads. like this. That's a big machine. All right, so if we start application as usual, without Docker container, we can see nice Java behavior. It will show us most of the time out of memory error. And we are able to handle it even inside the JVM. But OM killer gives us no chance. So you see it already happened. If I would pass like less memory, or just be lucky enough, we could see that what application does. Oh. No. It is already died. No. So it does GC all the time. So it spends all the time in GC and then it dies. And here we use a standard JVM tool, but it works in a couple diff JVM running not in a container. And in case of JDK 8, it won't be able to handle JVM running in a container, so we need a modern 8 or newer version. So how much memory do we need? That's a question, right? So we use containers to put some limits, and it's good to choose wisely. We don't want to waste memory, and we don't want to see our services dying, right? The simple way to know it is to run our application with native memory tracking and to look how memory it actually uses and for which purpose. So you see native memory tracking is enabled, and we'll use JCMD at the right time to look at the application and to check the memory. And the right time is, from my perspective, is after it starts and is ready to accept connections, etc. Again, we're looking at JDK 8, so I'm running this process not in a Docker, but I do this to figure parameters for Docker. There are other approaches, like some scripts from Fabricate and other producers that apply heuristics to calculate how much memory your application actually needs. But from my perspective, it's not quite right, because you can have huge meta space, you can have huge heap. You can only find it out in the runtime. So now application starts, and we'll check native memory. So look at this. We found out the process ID of our application. Again, it's not Dockerized, otherwise JPS won't help us. And we use J command to look how used memory is distributed by areas. Someone may calculate it right now, but what we basically should do is to take all committed memory, extract committed Java heap, and extract committed GC memory. It will result in about 290 megabytes, which is reasonable. It's a microservice, right? I used to program on the machine that had less memory. Anyway, so we can start our microservice with more reasonable limit. But we won't do that. Let's try something more brave, right? So here they put memory limit of 128 megabytes. So how do you think what will happen? Will it start? Let's just check. All right, it works. Let's look at Docker diagnostics. The basic diagnostic tool is, of course, Docker stats. So you see, the process happily lives with the memory less than it requires. Is it normal? Maybe let's stress it a bit. It's still alive. What happened? Well, I can give you a hint. If it will run long enough, it will be killed anyway, by the same reason, because it will consume too much memory. But what kind of memory it consumes right now? And what numbers do we see in JMeter? Numbers are not that good, right? Even worse than in the beginning. And they will become worse and worse. So let's check memory of the process using system tools, like for example smaps or pmap. Get a beat, execute pmap, and we see that we actually use a lot of memory. This is swap. We haven't put a limit for swap for the process, and it just consumes swap memory, where it competes with other containers and processes. And from all perspectives, it's not very good. So the right way to start it would be to give it enough memory. Oh, yeah. To put a swap limitation. And in this case, it will happily fail if the limit on memory via -m is not enough. Just start. Let's check it. Here we are. It was killed. So let's disable swappiness. Let's put enough memory, like 700 megabytes, and start our service. Let's even run JMeter. And look at Docker stats. That's now reasonable. With a lot of memory, but that seems enough. It's close to the limit, but the service is alive. Know your limits. Maybe it's too close. Time to do GC? No. All right. I think it's not very good that our process started for 20 seconds. Have you noticed it? I notice it every time that I start Spring Boot application, especially on this machine, especially if I limit number of CPU resource. So we can do much better. like this. Here's the FinJar. FinJar and all the libraries unpacked from the FAT jar. So we set class path here. We use now JDK 11, right? That knows about container limitations. And we also limit number of code cache, but here we sacrifice the peak performance because we disable server compiler and use only client compiler. So we don't profile, don't re-optimize, just compile methods. But for this services, it's fine. And in this case, we put limitation only into 156 megabytes. Let's look again. Let's start JMeter. Let it work. So let's check the startup time. Have it started? So it's around 10 seconds now. Much better. I don't see the number, but I just remember it. Does anyone see the number? Oh yeah, I see it. That's our 10 seconds. And we consume much less memory. Much less memory. But from the other side, the peak performance measured by JMeter is about the same. That's not bad. So we saved some money. Now, what other options do we have to try to speed up startup of our service? How do you think? What's the problem? What happens on the start? Yeah, class loading. So we load all the classes, resolve dependencies, scan them. A lot of class loading, actually. The canonical way for hotspot and for some other virtual machines to use class data sharing. So we can just try it. And it actually helps. But again, here FinJar helps us. Because when we work with FATJAR, classes visible and loaded by system class loader are just few. We'll look at numbers, but the difference is impressively big. So we need all the class path. What's worse, we need it in this form. This is actually an exploded result of cutting some file prepared in more or less automatic way. But we need static class path, otherwise AppCDS won't work. There should not be any wildcards, folders, extension class path, nothing. And you see a lot of proxy classes and also classes that are too old being skipped. But a lot of class data is generated and we can use it. So the process is fairly simple. And here I use Docker container to generate class data archive to the volume mounted to the Docker container to reuse it afterwards. I could put it inside the image, but in case of volume, I can share it between multiple instances of the same image. Let's look on some artifacts. Shared archives. That's an archive for Yeah, that's probably not the right one. For the fat jar, and that's for thin jar, which is twice as big. And if you look at the number of classes, so it's only 2.5K classes for fat jar, but much more for thin jar. Almost 3 times more. So, will it help our application? Yes, it will. Let's just start and look at start time. The command is huge, but the main part here is that we enable class data sharing, provide shared archive, and we need exactly the same class path. We cannot reuse archives between different applications because JVM checks that our class path is the same. So we probably can start different main class, but the class path should be the same. Now it will be really fast. But maybe someone were interested and studied other options, like I personally like GraalVM native image, where such an application will start immediately. But the problem here is that not all Spring features are supported. The implementation is not fully specification compatible, is not the same hotspot. So a lot of problems. Again, there are growing competitors like Quarkus or Micronaut using the same technology. That's interesting. In their case, they combine class data sharing with AOT compilation of your business logic code. And Hotspot also has AOT compilation, and OpenJDK has it available for free for a few releases now. And we can use it here, but it won't help. You can refer my talk about AOT compilation and its performance. Unfortunately, it's not so easy to find a scenario that this implementation will really help for startup of such a service. So that's our best result so far. What's interesting here is that we also improved footprint because then we use class data sharing. Footprint of even one instance is slightly better than the case when we don't use it. All right. So, what we've seen so far. We've seen that we might create one of small base images really in a really simple manner using base images of Liberica. We can discover what happened with our poor service that died silently. It's not so hard. There is also a Docker mechanism for that. That's, from my perspective, a bit less convenient, but it may give you information in a more flexible way. We can use native memory tracking to find out what are memory limits for our application. We can stress our application running in a container. It can die, but again, we can diagnose that. We can find out what happens with SMOP using system tools. We are running on Linux, so We can use system tools for everything, and also some other cool stuff like stuff for profiling. Applications may start slow. We can try to speed up. So here are a couple more words on AOT. One of approaches we can apply is to log all methods that were executed, for example, until application is started, our microservice. Then we can, But we have to process the data to make it again available for hotspot. So unfortunately, different parts of hotspot sometimes use different formats for everything. There is also one more format, compilation log. You may want to compile ahead of time methods that were JIT compiled because they're hot. In that case, we'll have to process compilation log. In this case, I process log of touched methods. Here's a script. You will find it in slides. That's just a very part of transformation of one format to another. And then an important thing, if you want to use AOT, you'll use JOTC tool. And here it started using the same container, using the same configuration. And there are defaults. You can see that it's JDK 11. It knows limitations. And particularly, you won't be surprised, but I'm not sure about this particular case, but at least in some experiments, default GC was serial. Sorry. So you either have to know exactly what parameters are being used inside Docker container by printing flags, and then providing them to JOTC and using the same JDK to get your AOT library, or just use the same container configuration. So Java defaults will be the same. And if we'll look at all the native libraries, you can see that library generated from FATJAR as a jar is tiny. But if we use FinJar, we can generate two libraries, one for Java-based module, which is significant, and one is for application methods being executed during startup, which is also impressive, but that won't help us to reduce time. From the other hand, we can share this library between processes. It's a shared library. That may help us to reduce some footprint. Sorry. Okay, so we also saw AppCDS, where we use FinJar, we used ClassPath. That's not a dynamic, not a lib folder, but all the jars listed one by another. Using Docker in the same container, you're able to get the list of classes in the very same way as a regular, and to get the shared archive. Here we are not, we don't have to use Docker container. We could use just a regular execution to start JVM as always, but we have to keep paths the same. So then we'll start with libraries, the same class path should be the same, so it's much easier to use container, right? Because that's the same path on volume. And finally, we got some improvements. We sacrificed peak performance, but we got 6 times less memory requirements. It's even less. It's around 100 megabytes, but to let it not die under the load, 128 is fine. And we made speed up in startup, which is now reasonable and is under 10 seconds. So what are interesting conclusions here? Mature systems met our expectations. We are able to use Java and Docker together and to get benefit out of that. But please, please, please use latest updates and switch to newer versions because they are really nice features and, of course, security fixes. You can get it all for free using your regular processes like Docker pull. Look who is the provider of your base image. And it's possible to tune resources for our needs. Maybe I can just show you an interesting experiment. First of all, one more thing. All you've seen is running on ARM server. So this ARM server has a lot of cores. And a lot of memory. That's why swap was so sweet for that application, because it's huge. But it also has a lot of disk and, well, many resources. So we can start a lot of containers sharing the same shared archive instances of this service mapped to different ports with JMX enabled, JFR enabled, all on ARM server. And let's just do that. So which one is limited to around one CPU, and we just start a lot of them very quickly. To me, that's impressive. No Docker Compose, just shell scripts. Okay, that's all I wanted to show. Maybe let's switch to questions, if you won't mind. Are there any questions? Okay. All Docker-related fixes from JDK 9.11. Well, that's a question about any backport, how well it's backported. I would say you won't notice a big difference between 8 and 9 and 10, but for 11, I'm not so sure because it's harder. America 8 also contains libtas and non-security. Here I just can't answer you about particular vulnerability. I think, I don't know the name of this library or the vulnerability. Yeah, really? But what I can say that you can get the latest security update. So if it's known and fixed vulnerability, you can get latest security update that it's already fixed. What's the license? It's the same license, JPL with class path exception. We are on the public license. We are public licensee of Oracle. So you can just take it and use it in your production. That's free. And you'll get security updates for long-term supported releases for a long time. Our option is that you can switch to commercial support and get support and all fixes made for you upstreamed to OpenJDK. But you don't have to do it. All right? Any other questions? Okay, then we can just finish. Thank you for your attention. Nice to be here.